Welcome. Today I will present attacking and improving the Tor directory protocol. Let's begin by introducing Tor, also known as the onion router. Tor is the largest anonymous communication service to date. It sees around 4 million users daily. How Tor works is that in the first step, you will use a Tor client that obtain a list of all the volunteer nodes from a directory server. Then your Tor client will pick a random path from your computer to the destination by routing your traffic through 3 different randomly picked relays. In this instance, we pick the 3 relays here as shown in the figure. So there are easily tens of research that focus on how the 3-link hop is secure or not. In this paper, we seek to answer the opposite question of whether or not the first step is secure or not. To answer that question, let's begin by diving into Tor directory servers and their mechanisms. It turns out that Tor directory servers have been improved over time ever since Tor was first developed. In version 1, which is the earliest version of directory servers, there are just a bunch of volunteer servers that collect relay information and publish them. The client will pick an arbitrary server and fetch that information from the server. The problem is that somehow introducing more directory servers means there's less security. As the current Tor directory protocol states, in this version, every directory authority represents a trust bottleneck. If a single authority were to lie, it could make clients believe an arbitrary view of the Tor network. In version 2, Tor people has noticed this drawback, and now the client will download from multiple servers and aggregate this relay information locally. The problem is that ever since then, the directories has grown quite large. For now, the directory is about 5 megabytes in size. Multiplied by 9 authorities and 4 million users daily easily makes it 180 terabytes daily. That's far larger than what Tor people would like to see. Also, the current Tor directory protocol mentioned the partition attack, which means that if some directory authority were to be censored in some location, the client might have a different access pattern that allows them to be partitioned. Since 2007, Tor directory servers have migrated to version 3. As of now, there is a small set, 9 as of now, of semi-trusted directory authorities that sign a summary of their view every hour. They will send this signed summary, also known as a status vote, to other authorities. Once every directory server receives all the votes from every authority, they will compute a result, an aggregation that's known as a consensus document. They will then sign on this document and broadcast the signature to other parties. Now, any directory authority could simply send their consensus document together with the signatures to convince the client that they have the valid document. This is proposed around 2007. If we think of it as some agreed information that's made public on the internet, that makes it kind of like a blockchain. In that sense, it's the longest running blockchain, even earlier than Bitcoin. So we have obviously dig into how the Tor directory servers work by their code, and we draw out this diagram. In this diagram, we can see the first step is that directory authorities here will collect information from the relays. They will then broadcast what they know to other directory authorities. Tor, think of the scenario where there might be some network latency that causes the vote to be lost. So they designed a step named as fetch votes that allow a single directory authority to ask around other authorities to see if there are missing votes. After the authorities finish collecting the votes, they now do what's known as a computing consensus, which they will compute the consensus document as previously described. Once they have finished that, they will broadcast their signatures to other authorities. And once the broadcast of the signatures are completed and the backup measure of fetching signatures from other authorities are completed, the directory authorities will be able to serve their directory consensus documents to clients. With this out of the way, a natural question to ask is how secure the current Tor directory protocol is. Well, empirically, we have seen the consensus protocol suffering problems from network stability and DOS. In 2010, we have a singular case where Tor failed to make a consensus. And 3 years ago, we also have the problem of directory authority getting DOS and using an unsustainable amount of bandwidth. But that's in benign scenario where there are only outside attackers trying to compromise the protocol. Let's consider a scenario where there are bad actors hidden among the directory protocol. Here we introduce what's known as an equivocation attack. In this mock example, we have 3 authorities, where E up here is the bad guy. H1 and H2 are good guys, but they have different view on some property of some relays. Let's say H1 believes it's 0 and H2 believes it's 1. What E can do is what we know as an equivocation, where he will vote 0 to H1 and vote 1 to H2, thus causing H1 and H2 having a split view. Now, from an H1's perspective, he will see that 2 people voted for 0, so he will sign on 0. From H2's perspective, he will see 2 people voted for 1, so he will sign on 1. This creates a difference in the signature they created. A naive application of this attack creates a liveness attack, where the attacker can simply find an arbitrary thing that authorities split their votes on and equivocate on it. This causes the correct authorities to sign on different things and may cause the division to result in a no valid consensus document. What's more is that the attacker will be able to sign and publish one of the consensus documents and make the other unpublishable, hidden. The client will observe no difference as a consensus with 5 signatures is valid too. But that allows the attacker to sign on the other consensus privately and obtain 5 signatures without public knowledge. This will allow the attacker to circumvent all public detection measures that Tor is unfortunately heavily reliant on. We give a very specific example here known as a bandwidth attack. In this example, the attacker will publish a honeypot rally with very large bandwidth, and he will attempt to trick the client to use it with very high probability, as the client are naturally inclined to use a rally with very large available bandwidth. This is usually a loud attack, as it's very detectable with public tools. However, with our described equivocation attack, the attacker can make it silent. We tested and verified the result on testnet. Here we briefly demonstrate the pickup bandwidth code, where we want to draw attention to this specific part. It says that any 3 directory authority can dictate the bandwidth of a new board rally. We also showcase our attack result here with a very large bandwidth and how this consensus document were not able to be published because of insufficient signatures. We also present an attack known as the civil rally attack. In this attack, the attacker does not publish one rally with very large bandwidth, but a ton of new honeypot rallies. It's also usually a loud attack, as publishing a ton of rallies tend to draw attention, but with our attack, this approach will no longer be detectable. The main takeaway here is that Tor makes heavy use of the public audit mechanism, and with this kind of attack, we're able to circumvent it in different ways. I think it illustrates a meaningful relationship between real-life attacks and theoretical security, as a protocol that's not theoretically sound might have different attack in all kinds of different ways. One point that's worth noting is that we may not even know if such an attack ever happened in the past, as we do not have enough log to analyze how consensus is formed. So, how can we fix and improve the protocol? Reactively, we can try to detect irregularities from now on. Towards that end, we designed tor1, an online equivocation detector. It's a built-in detection mechanism to see if irregular activities take place. We merged this into the Tor code base, and it's now currently live online. We showed that the performance of tor1 is good, that it only requires around 5 minutes to generate one report, but we also list out some of its limitations. The most important one is that now the client has to place trust on the detector, creating a new trust bottleneck. And the detector, if compromised, can cause the client no longer to be able to detect such kind of attack. Proactively, we can also improve the protocol to weed out this equivocation thing entirely. Toward that end, we first try to analyze the problem we are solving. Well, obviously, we want to solve the problem and produce some sort of consensus document from a set of input. We figured that the way Tor actually computes the document is pretty complicated, so we decided to turn to local computation as what they are doing now currently. We figured that this is known as an interactive consistency problem, where every server wants to output the same set of input values. This is done by parallel Byzantine broadcast, which allows a potentially 4D server to broadcast to everyone and have everyone agree on the value being broadcasted. We treat our system model as in a bounded synchrony setting, which is the same as the current Tor protocol with a runtime of 150 seconds. We assume the attacker is Byzantine, that they can try to behave arbitrarily and break your system. We're targeting 2f+1 security, which is the natural bound given by these two conditions. We also noticed some particularities of Tor. One is that it's a very low number of nodes. It has a very large document size and some somewhat outdated code and PKI structure. We also want to minimize the attack surface that tries to be as fast as we can in the optimistic case to avoid any potential DOS from taking place. With these goals in mind, we designed diecast, which has optimistically 4 rounds with a communication complexity of n cube. It uses 2 phases, a bootstrap phase and an agreement phase. In the bootstrap phase, we try to weed out equivocation and give everyone a good behaving certificate for not having equivocation. And in the agreement phase, we try to synchronize everyone so that there is no crash issue involved. If there is no crash, then in the best scenario, everyone can agree in 2 rounds. And if there is crash, then unfortunately it may take up to f+1 rounds, which is the same as the previous upper bound given by Dolliff-Strong. Here we showcase a diagram of our protocol. You can see here is the bootstrap phase, in which we have a propose where everyone sends their votes out, and then we allow everyone to sync up on each other to see if there's equivocation. And in the agreement phase, we simply synchronize the certificate among each other to make sure that no crash will cause different people to have different views. We implemented it with C code, the same as the Tor code base. We used a technique known as a message compression. Mainly, we noticed that the difference between two consecutive consensus documents tend to be small. And by only broadcasting the difference, it allows us to cut message size drastically, which allows us to achieve a performance that's comparable to the current protocol. We have coordinated disclosure with the Tor team. We first reported it in 2022, and it's acknowledged on May 6th, and we have shipped a detector 1 year later. And as for the protocol, Tor is migrating to a Rust base currently, so we are trying to implement that in Rust once they have got around to the directory authority part, and we're looking forward to in collaboration. I had the honor to work with a lot of my wonderful collaborators for the project, and I will summarize our paper now. We first discovered a protocol design vulnerability in the Tor consensus protocol. We developed Tor EQ, which is a mitigation solution that allows us to detect irregularities. We also prototyped diecast, which is a security improvement. Thank you.